So before I begin in earnest, I want to thank Ed Pegg because the model that I'm about to glance over very briefly is his. In fact, the only thing that I'm going to say about his model of fair dice is that it implies that in order for a die to be fair, meaning that when you toss it, it has an equal chance of landing on any side, one of the requirements is that every face be exactly the same shape and every face have the same relationship to the center of mass that every other side does. And that should be sufficient to prove that a polyhedron is going to be a fair die. Now this is an example of one. I have a 12-sided figure that is made up of two 6-sided pyramids stuck end to end. And as you can see, all the faces are the same. And they all have the same relationship to the center of mass. So our theory predicts that this should be fair. However, it also is boring because this shape is also an isohedron, which means that every face has the same relationship to every other face. There's a rotation or a reflection that will map any of the flat surfaces to any of the others, which means that a simple symmetry argument will tell you that this die is guaranteedly going to be fair. What I wanted to do was take a look at some other shapes that were possibly fair but not isohedral, meaning they all had to have the same shape as the side of the die, but not have the same relationship to each other. And one such example that Ed talked about in his paper is this die. It is again a 6-sided pyramid on one end and a 6-sided pyramid on the other, but there's this middle layer that's an antiprism. And by choosing the heights of the sides of the triangles correctly, I can set it so that all of the vertices lie on the surface of the same imaginary sphere, which means that the height above the center of gravity for each face is the same. And if you were to map the center of gravity onto the point on the triangle, it would be in the same location. And so the theory says that this die should be fair. So I tested it. I had one 3D printed up and I rolled it a few hundred times and it's broken. Unfortunately, the model makes an assumption that as a die bounces on the table, it is going to tip over each side more or less at random based on the angle that is formed from the center of gravity. But that's not what happens when you toss this one. If you were to just drop it onto the table, actually the math works out fine. The statistics that I gathered worked out fine. But when you toss it with any degree of spin, it tends to roll along that antiprism column. And even if when it's on one of the two pyramids, it'll tip over and continue to roll along that axis, which means that these sides become much more likely to be landed on than these sides. So it turns out not to be a fair die, and not surprising because, as I said before, it's not isohedral. The question then becomes, are there any other candidates for non-isohedral dice that might be fair? And at least at the time of the writing of the model, that was an open problem. And it's surprising to me that it is, because there's a very simple modification that you can do to our isohedral D12 that's probably familiar to you guys. If we pick the heights appropriately, we can make the cross-section a perfect square and just rip the thing in half, give one half a 90-degree turn, and stick them back together. Every face is still the same shape, and every face is still the same distance from the center of gravity. But now we have a very non-isohedral object. As you can see, it's all lopsided and cockeyed. So I wanted to test this one too, and I had one printed up, and I rolled it a few hundred times on assorted different surfaces to adjust for different bounciness and different throw styles. And after a few hundred rolls, what I got was statistically no different from what I would expect from a normal D12. And not content with my small sample size, I decided to print up 400 more of these and roll them collected 12,000 times, and still have exactly the same statistical distribution that I would have expected from a normal D12. And so the question now I have is this die fair? And the answer, best answer I can give you is maybe. I don't know. The fact that this one came up as false says that the model needs work. And I don't have a better model, but so far all I can tell you is this is fair enough for practical purposes. And I'm hoping that one of you will be able to prove it one way or the other and let me know. That's it. Oh, and by the way, those 400 that I printed up to roll, I'm giving each of you one of the experimental subjects in your gift exchange. So.